Okay, good morning everyone. Welcome for our training session of the FirEUrisk project on the extreme fire behavior and wildland-urban interface management. My name is Domingos Viegas. I'm the coordinator of the project, and I will give a brief presentation of FirEUrisk for those of you that are contacting us for the first time. FirEUrisk project is an horizon project that is now in its final months. We have less than 5 months to go till the end of the project. So we are presenting the results of our project in these sessions. The objectives of our project were quite wide. We were requested by the call to develop, test, and disseminate an integrated science-based strategy based on the risk assessment and aiming to reduce current fire risk conditions, and also to prepare ourselves and the community, and in particular Europe, to adapt to future management strategies, taking into account future climate and socioeconomic changes. This we try to do in close collaboration between researchers, practitioners, policymakers, and citizens. And this training session is also directed to that, let's say, to share our knowledge, our results, and also to get input and feedback from you about their relevance and interest. The overall topic of the project is shown here. We are looking at the problem of fire risk, wildfire risk, putting the risk at the center, let's say, concentrating our activities on the concept of risk and its components to better understand and assess fire risk, to work on reduction and adaptation. The project had this structure with 8 work packages. 3 of them more technical ones on risk assessment, risk reduction, and adaptation to future regimes. And we had always the purpose of integrating all these concepts and then to demonstrate and test them in pilot sites and to propose measures of policy that could serve the different regions and countries in Europe. And this training session today is in the scope of work package 2 on wildfire risk reduction. And in it, we tested different risk reduction strategies. We looked at the problem of ignitions caused both by human activity and also natural ignitions, but we aim to reduce the human-caused ignitions. We worked to increase the socio-ecological resilience and also to learn from previous extreme events. One of our goals was to improve training and preparedness of stakeholders, especially in dealing with these extreme fires. The project is being coordinated by a steering committee. These are the 4 persons that are the members of this steering committee, and we have been working together in the management of the project. We had partners from all over Europe, as I showed, and we had demonstration areas in different countries where we test different concepts. We had 5 pilot sites in different parts of Europe, 3 of them in Southern Europe, 1 in Central and 1 in North. And we considered that the whole European territory was also a test area for our project, for our concepts. This is the Gantt chart of the project, and as I said, we are now just near the end of the project, only 5 months to go, but the most part of the work is performed and the results have been achieved. So now I leave the floor to Valentina to introduce the webinar and to start the presentations. Valentina.
Okay, can you see my screen? I think yes. Good morning, everybody. Thank you, Professor Viegas, for this introduction. Okay. Can you hear me? Sorry. Yes. Today, this training event will focus on guideline and tool for extreme fire and fire in the wildland urban interface management. And one of the aim, as also Professor Viegas said, of FirEUrisk is to organize training activities in several forms. For example, practitioner workshop or focus webinar or hands-on training. The aim is to support the sharing and the inception of the project results among the researcher and the actors involved in fire management. So far, we organized 2 trainings in 2023, focusing the first one on fuel classification system and fuel mapping, and the second one on mapping the wildland-urban interface. Everything, the material we developed everything is available at this web page, and I will share you the link in the chat later on. And today we are focusing on this other topic, guideline and tools for extreme fire and fire in the wildland urban interface management, with the aim to bridge the gap between researcher and operational practice by sharing the guideline we develop and the tool that we develop in the framework of FirEUrisk to improve preparedness, to contribute, let's say, to improve preparedness and response against extreme fire and also fire occurrence in the VUE. The training today is divided in 3 sections. The first one is more, let's say, broad, general, in order to give you a better understanding of the dynamics of fire, extreme fire, and specific risk also associated with the VUE. And we will have 3 presentations. Then we will have a second part focusing more on the demonstration of a decision support tool that have been developed in FirEUrisk. And then we will have an interactive discussion that include either the question and answer section and the feedback from the participants. The speakers of today are very well known, let's say. For example, one of the speakers is Professor Viegas, the coordinator of the FirEUrisk project and director of the Association for the Development of Industrial Aerodynamics, the ADAI. Then we will have Sébastien Lahaye from SAFE France, coordinator of the European project coordination at SAFE Cluster and president of Varus & Company. Then we will have David Caballero, which is a freelance consultant on risk assessment and also instructor at the National School of Civil Protection in Spain. Then for the demo section, two presentations will be delivered by Carlos Viegas, assistant professor at the University of Coimbra, and Ana Miranda, full professor at the Department of Environment and Planning at the University of Aveiro, still in Portugal. So I think that we can start without any other delay, and I would like just to remind you that if you have any question, you can write it down either in the chat or in the question and answer section. I would like also to ask you if you can write the name of the presenter you would like to respond to your question, and then at the end of all presentation I will read your question, and the speakers will present. And also I would like to remind that everything will be recorded, and also the presentation, but also the question and answer section will be shared later on through the project web page. So I give the floor to Sebastian Lahe. Thank you.
Thank you very much, Valentina. Can you see my screen correctly?
Yes.
Yeah, fantastic. Hello, everybody. First thing, I'm very sorry, but a kind of a virus affected my voice for the last few days, so I will try to make this presentation complete, but as you can hear, probably my voice is not very strong, so maybe I will shorten a little bit the presentation. But anyway, if you have any question or anything is not clear, don't hesitate to ask question on the chat. So I'm Sébastien Lahaye from the SAFE cluster in France, and actually I was coordinating this work package 2 on fire risk reduction. Today we'll introduce the question talking about extreme fires, but also extreme fire behaviors, and we'll see the impact of that. So first, let's dissociate extreme fires with extreme fire behaviors. And let's talk firstly about normal fire with two very simple questions. With no wind, what does a fire on a slope? And the second question, when the wind comes from the north, where does the fire go? Obviously, the answers are very simple. Talking about fire on the slope, everybody knows that the fire goes up because of the angle of the flame with the slope. That's the normal behavior of the fire. With the wind, obviously, everybody knows that when wind is coming from one direction, it's pushing the fire in the same direction. So that's the description of a normal fire that is really linked with weather, fuel, and topography, and with kind of a linear relationship. That is that the more wind, the more rapid is the fire, the more slope, the more rapid is the fire, and the driest or the more fuel, the more active is the fire. This is the basic understanding. But when we talk about extreme fire behavior, we talk about something different. And extreme fire behavior does not mean that you have an extreme fire. But extreme fire behaviors can lead to extreme fires. And here is the illustration. Extreme fire behavior is something that happens at a local scale, but when you aggregate extreme fire behaviors, you converge to something very different that is an extreme fire. And actually today, we'll more talk about the description of extreme fire behaviors and the consequences of them. We'll consider today different phenomena, not in details, but the phenomena that are listed here. Sorry. First thing, when you don't have flame attachment, we mentioned that the fire normally climbs a slope. It goes up the slope, and let's say that more or less the steeper the slope and the more rapid the fire. This is right, and this is kind of linear, but up to a certain threshold. This threshold has been established around 20 degrees. There have been many researches in the last years that have demonstrated that when the angle of the slope is steeper than 20 degrees, this is no more a linear relationship that you have. you have kind of an attachment of the flame that is suddenly attaching the slope, and that makes the fire very intense in a few minutes, sometimes few seconds. And this has been observed in different configuration, on different entrapments. This one is a picture of an entrapment in France, in Corsica in 2000. And as you can see, it's really kind of a sea of fires that invaded the slope in few seconds. Canyon effect. This is something that Professor Viegas' team has studied a lot, and I'm quite sure he will come back on that, and the team will come back on that in a few moments. But they have demonstrated that when you have a canyon configuration, you have very extreme acceleration of the fire and very intense fire. Coalescent. What does that mean? When you have two fires or two fronts of fires that approach and that are about to collide, what happens? The same as in canyon. You have a sudden merging of fire lines that creates a very, very intense burning. It's not linear, it's kind of an explosion of the fire when the fire lines coalesce. Another phenomenon, vorticity-driven lateral spread, that has been studied a lot by our colleagues in Australia. They have demonstrated that when a fire reach a ridge, the top of a mountain, a ridge, and when the angle, when the wind is more than 40 km per hour, and that the downslope is steeper than 20 degrees, you don't have a fire that just normally goes down the slope. You have very intense spotting activity that happen not only in the direction of the fire, but also laterally. And this is an illustration, but this has been observed also in some fires. As you can see here, the fire is arriving from the right. It climbs the slope, and when it arrived on the ridge, it produced spotting laterally on the left here. I won't go more in detail on deep flaming, but I encourage you to look at Mark Finney, our American colleague, description of an entrapment, an accident in 2020. You would see that's very interesting. When flame are not, when the fire front is not a line, but it's very deep, it's very profound, this is also a big challenge. And mass spotting, you can understand that when you have not only one spot fire, but a very intense spotting activity, that is also very challenging. Okay, there are more intense extreme fire behavior to describe, and my colleagues from ADAI will come back on that today. But something also interesting is that obviously they are not isolated, because some extreme fire behaviors can lead to other. And as an example, flame attachment would create deep flaming, and also in a canyon you would create flame attachment, and so on. So that there is kind of an escalation of phenomenon that can happen, and that can lead to two things: adverse behavior for firefighters and extreme fires. Now let's talk about the impact of this extreme fire behavior for firefighters. The first thing to consider is that obviously the responders have limits, physical limits. Our colleagues from Spain, from Catalonia, have established their limit. These are the limits of the Catalan Fire Service. So maybe it's a bit different depending on your country and the trucks and the planes you used. But anyway, they mentioned that with flame length more than 3 meters, you cannot address that. with a rate of spread more than 2 kilometers per hour, you cannot respond. And also when you have active fire crowding, you cannot fight the fires. So whatever the limits, there are limits. That means that faced to extreme fire behavior, direct attack is more or less impossible, and you have to find other ways, such as indirect attack, as an example. Few words about entrapments. Again, the teams of Professor Viegas has demonstrated in 2009 and described several accidents in Europe. Probably most of you knows this work done about 15 years ago by the team, and they reproduced these studies several times. Talking about statistics, we know that there are very consolidated statistics in the US and in Australia that demonstrate that in the last century we have had a lot of entrapment of firefighters. Statistics are less consolidated in Europe, but anyway, considering only France, we know that during 30 years, at the beginning of this century, we had about 30 firefighters that were reported death because of entrapments. We studied these entrapments across the world, reviewing some of them in Australia, in the US, and lots of them in Europe. And I will not develop on this table. We can have some chat on that if you need, but I will focus on some results that we found in the next slides. And I will focus on the lessons learned for firefighters. The first thing is that, as we mentioned, on slopes steeper than 20 degrees, you can expect flame attachment. And we have demonstrated that in topography environment, in mountainous terrain with fires, this has caused many entrapments, and most the entrapments were in that situations. Which means very basically that when a fire is on the slope, you have a safe zone that is below the fire, but as soon as you are above the fire, you can consider that as a dead man zone. Even if as you are very far from the fire, you should expect a very strong escalation of the rate of spread. Vorticity-driven lateral spread, we have described the phenomenon, and so that this is something to consider when you have a wind-driven fire, a fire that is pushed by the wind on the mountainous environment. You can expect this phenomenon of fire enlarging after the ridge when the wind is strong and is impacting the ridge perpendicularly. And then convective fires, the most extreme fires we have with pyro, cumulonimbus, and so on. With these fires, the thing is that, and these fires, as you know, happen when you have a very severe drought, and especially with high temperature, low relative humidity, and they are accelerated by unstable atmosphere. These fires are evolving so erratically, so dramatically in many directions that you can expect long-range spotting in any direction. And the finding there is that it's very difficult to find a safe place, but you should be very cautious about the development of the fire, and sometimes you can expect entrapment even if you are not in the main direction of the fire. How can we integrate that findings in our procedures? This is something we have to integrate at several levels. From fire analyst level, the most expert people, to the crews and full command staffs. At every single levels, there are things to take, very basic things that you can take as crews, such as identifying slopes prone to fire, to vorticity-driven lateral spread or to flame attachment, or recognizing a wind-driven fire from a topography-driven fire, as an example. Sorry, I'm not able to comment more on that table, but I let you read it. And I guess we can disseminate the materials anyway. And finally, and I will finish with that, to mention that with normal business, obviously the responders do land management, do training, preparedness, and on-site response. And this is kind of the normal business. But considering these research insights, our recommendation is to go a step further. And as an example, talking about land management, we used to consider that fire tracks have to be built on slopes regarding the wind. Now we have to consider that on slopes steeper than 20 degrees, faced to this extreme fire behavior, we have to consider very wide fuel break on slopes steeper than 20 degrees if you have fire trucks there and if you want to have a firefighter able to respond there in safety. This is just an example, but as you can see, at every single level, you can integrate these very basic outputs from our researches. And I will stop that there. And lesson learned, obviously, is very important things. Thank you very much, and hopefully that was clear enough for you, but I'm happy to take question in the end of this session. Thank you very much.
Thank you, Sebastian. I really hope you recover fast from this virus. And so, as I wrote in the chat, if you have any question, please feel free to write them in the using the chat or the Q&A button, and also please indicate the speaker your question is directed to. And the next one from the agenda would have been David Caballero. But unfortunately, he warned me that he had some difficulties in connecting. So I would like to Professor Viegas if he can present now, and then we will try to solve David Caballero problems and try to let him present later on. Thanks.
Okay, Daniela. Sorry, Valentina. Thank you very much for introducing me. I'm sorry for this difficulty with David, but we'll try to sort the program out. I would also like to thank Sebastian for his talk. It is let's say, a good introduction for what I'm going to speak as well. Actually, I'm going to continue what Sebastian presented, let's say, to look at this extreme fire behavior modeling. And as he already suggested, I will also cover some of his topics. The contents of my presentation are these ones. This is the structure of the presentation, and I will go directly to the introduction. I will present the work that was developed by my team, in the scope of a FirEUrisk project, especially on the topic of extreme fire behavior. I'll start reviewing some concepts, as Sebastian did as well, and then go present our work on extreme fire behavior. This is a topic that is very much related to fire safety, as Sebastian also mentioned, and to predict the fire behavior that has been the driving forces of our research. As you know, here in Portugal, we work very much not only with analytical and computation tools, but we go very much to the experimental side at our lab. We have these different facilities where we can study very carefully some aspects of fire behavior. We do also field experiments where we can try to understand better what is happening in the fire at a larger scale. And further, we also go to the field to observe real fires, and we study them. And it's actually confronting the observations that we make in the field with our knowledge that we find ideas to other new research. Going back to this concept of extreme wildfire events and extreme fire behavior that Sebastián already addressed, I'm not going to discuss this very much, but we are dealing mostly with extreme fire behavior that is out of normal process in fire behavior. And this has been discussed very carefully in a paper by Terim et al., in which the conditions for having extreme wildfire events and extreme wildfire behavior are listed with multi-criteria. And in this table, we can see different categories of fires. And you can notice that one of the criteria is the fire line intensity. When this fire line intensity is above 10,000 kilowatt per meter, it is said that we have extreme wildfire behavior. And it's also mentioned that the fire behavior is chaotic and it is unpredictable, the fire spread. Okay, this is the problem that we are trying to address, to see if it is possible, to address this. I must apologize, I'm having some problems with my camera. I suppose that you cannot see me, but anyway, I'm here. So this concept of fire line intensity is very important, and you all know the definition of it. It is the product of these three terms. The rate of spread is the most important because it can vary 4 orders of magnitude. But the other two parameters also change, of course, in the field, but they change in a much less level. In practical terms, if you want to have extreme fire behavior, let's say above 10,000 kilowatt per meter, we need to have rate of spread in non-dimensional form. This is the non-dimensional rate of spread above 20 or 30. And this, although it can be reached by slope and wind, I'll try to show that it is mostly achieved by the dynamic behavior of the fire. So let's look at what is the dynamic behavior of the fire. We know that a fire is a system that interacts with the atmosphere and also with the ground, with the fuel. And so it can modify its shape and behavior continuously. And one thing that is very important to address, to remind, is that this occurs at all scales, from small fires to very large fires. But there are conditions in which this is more evident than in others, as we will see. For this reason, we proposed to consider the time as a factor in the analysis of fire behavior. So some years ago, we introduced this concept of the square of fire factors, that besides the 3 sets of factors that we usually consider, topography, vegetation, meteorology, we added the chronological time to take into account. Regarding the 3 factors, the topography, usually people consider only slope, but we proposed that the terrain curvature should also be considered because it modifies very importantly the fire behavior. The vegetation, we can use different parameters, but I would like to recall as the most influential, the moisture content, and also one parameter that is not very much addressed, that is the residence time. When we are dealing with the dynamic behavior, we have to consider this parameter as I've shown. Regarding meteorology, we have 2 sets of parameters, the conditioning and the determining parameters. These are the ones that are more related to the fire behavior. And I will pay more attention to wind velocity as one of the most important. When we speak about wind in the fire, we have to take into account that the local wind at the fire is the addition of the atmospheric wind plus the fire-induced wind. And some people forget that this wind exists, but it sometimes may be much more important than the local wind, the atmospheric wind. One important property is what we call the basic rate of spread. This is the rate of spread of a fire front in horizontal and without wind case. And this is a reference rate of spread that we use to make the rate of spread non-dimensional. This is important because We can then see how the rate of spread varies with slope or with wind, as Rotterdam did, or with other properties, for example, the shape of the fire, because this is what will modify the behavior. This is a function that Rotterdam introduced, and as we know, it depends on the wind, on slope, and also on the flow bed properties. Rotterdam model and most simulation models consider only the average rate of spread. For example, for the effect of slope, if the slope is positive, there is a rate of spread that increases, and the average value is this one. If there is wind, it's also a positive effect if the wind exists and the rate of spread increases. But what happens is that the behavior of the fire is dynamic. In the laboratory, we can do these experiments very carefully. For example, if we make a point ignition in a slope, in this case a 30-degree slope, we observe the following. Well, in this case, it is the rate of spread for a 20-degree slope. These are 3 or 4 repetitions of the same test. And as you can see, the rate of spread with time is varying, it's oscillating, but it is increasing. If we go to 30 degrees, this is even more evident. The rate of spread oscillates and increases sometimes, and then at the end it decreases. For 40 degrees, this is even more evident. Let's say the rate of spread is always increasing for a point ignition fire. You see that the only parameter that is changing is time, and this is due to the dynamics of the fire. This is even more evident if we make a test in a canyon. As Sebastian mentioned, we studied very extensively this problem. And for example, in a canyon with this shape, with this line inclined 20 degrees, the rate of spread oscillates, but in average grows increasing. If you incline it at 30 degrees, the rate of spread suddenly goes up in what we call an eruption, and then it drops. Well, we'll have a look at this. Some time ago, we proposed this concept of oscillatory fire behavior, because you observe that the rate of spread of the fire is going up and down, oscillating. And this is due to the fact that the presence of the flame modifies the wind, and the inclination of the flame and the size of the flame is changing. And then there is a wind that is contrary to this main wind, and the flame gets straight, and the rate of spread is reduced. But then the process starts again, and we have another cycle. So this is a cyclic process that has oscillations. And we saw this at different scales. For example, this is the result of a laboratory test. This is a field experiment, and this is a real fire. You see that we use the same units, seconds, and the same units for rate of spread in centimeters per second in all graphs, but the values are very different. Anyway, the behavior is similar in all scales. We studied these oscillations in a large number of fires, both laboratory experiments, field experiments, and also real fires. And we studied the amplitude of variation, if you want oscillation of the rate of spread. And we found that this amplitude increases linearly with the rate of spread. You see that with our experiments, we covered 3 or 4 orders of magnitude of the rate of spread, and also the amplitude increases. This linear equation has this coefficient, and we can see that we can relate this coefficient with the amplitude of the oscillations. And the ratio between the maximum and the minimum value, it's shown here, depends on this coefficient of proportionality. For large fires, this coefficient is around 1.3. So we can see that in very large fires, the maximum rate of spread and the minimum can be in order of 5. This is an indication why it is so difficult to predict the rate of spread in real fires. And besides, we can see that results derived from laboratory experiments, as was the case of Rotterdam model, it cannot at all predict these large amplitude oscillations that we find in real fires. So we have to study real fires to understand these oscillations. We also studied the frequency of oscillations. The frequency is very high, so the period is small for laboratory experiments. For field experiments, it's of the order of 3 to 5 minutes, and for large fires, it is of the order of hours. So this frequency depends on the type of fire, but for each type of fire, it increases the frequency with the rate of spread, as we have found here. These are concepts that we are studying. They are not fully explored, but they can give some insight to the problem. Now, let's move to another topic. What is the analytical model for fire acceleration? We all know that the fire is a process where there are flames, so there are very strong convective processes here, and the presence of these flames will modify the fire. And what the fire is doing now may be very different from what it will be doing in a few minutes. We consider the presence of a flame in a wind. This flame will spread with this rate of spread. The presence of the wind will bring more oxygen, so the flame will increase, and the local wind will increase, and the rate of spread will increase as well. So this is the process of self-feeding of the fire. There are three basic assumptions in this model. First is that there is a one-to-one relationship, not linear, but one-to-one relationship between the local wind and the rate of spread. If we increase the local wind, the rate of spread will increase as well. The second is that the presence of the wind will modify the local wind. There will be a change of the local wind, and this is related to the rate of spread, and this will induce a change of the rate of spread. And the third thing is that this change of the local wind will modify the rate of spread in a given time. So these are the three basic assumptions of the model of the fire acceleration. I have derived here all the equations. I think I don't need to go through them, but just to show you that from those three basic equations, we can manipulate the equations and among them eliminate the explicit effect of the wind. And we come to this equation that has on one side the change of the time, and on the other side the change of the rate of spread. If we combine these two equations, we can have this derivative of the rate of spread with time as a function only of the rate of spread. And this is the basic equation of the model of analytical model of fire acceleration. We can also write that equation in non-dimensional terms. We can introduce these non-dimensional parameters. Here, this is the basic rate of spread, this is the residence time, and these are reference values of the wind velocity and the residence time. The other factors of the model, B1 and B2, are exponents. They are already non-dimensional, and we can write this equation of the derivative of the rate of spread in non-dimensional form. You see here that only when this product, this factor is equal to 0, the derivative will be different from 0. And this is equal to 0 when the rate of spread is equal to the basic rate of spread. This is equal to 1. In all other cases, we'll have a fire acceleration. So this is the normal case. Having that differential equation, we can integrate it. Of course, it's not easy to integrate it analytically, but we can integrate it numerically. If we know the values of the parameters, we can integrate. For this, we need to know the boundary conditions, so the initial conditions, and then we can determine the rate of spread at any time. This is the result of the integration for the case of pine needles. These are results from experimental tests, and we use some tests to determine the parameters of the model, then integrated the curve, and then we compared with the results of tests, and you can see here. Of course, this depends on the fuel. If we have a fuel that is lighter, that is like a straw, that has a smaller residence time, we have a different behavior. If you have shrubs like in the field that we have a higher residence time, we have a different residence time. But this is the experimental curve from that canyon in the field. You can see that the residence time is around 20 minutes in this case. So after this time, you have this acceleration. These are solutions of the model for herbaceous, for litter, and for shrubs. This curve is very important for practical reasons, because in the field you have this type of vegetation, and usually when we study accidents, usually the time of acceleration is of the order of 20 to 30 minutes, which is observed very often. Another boundary condition that also is in favor of very rapid acceleration is the junction of fires, as Sebastian also mentioned. In the laboratory, we study very extensively the merging of two oblique fronts, and I'll try to show here one such experiment, where you can see on the right video image and the left infrared image. You can see that this point here is spreading very fast due to the very strong convections that are created, convection currents that are created by this shape of fire. And this is happening, let's see, created by the convections induced by the fire. Actually, these are the cases in which we have the highest rates of spread that we have ever observed. For example, in such an experiment with 30 degrees slope, you see that the fire rate of spread goes up to 160 times the basic rate of spread. This is the non-dimensional rate of spread. And if the angle is 40 degrees, it can go up to 250 times. So it is a very fast spread that we can get in these conditions. We are studying the relationship between the flow and these oscillations. This is the result of experiments with a canyon at laboratory scale. And we can see here the trace of the flow at 2 meters from the ignition. And this is the rate of spread in the same scale of time. And we can analyze how these changes in the rate of spread are very much associated to the flow near the fire front where it is spreading. This is ongoing work now. Another topic I'd like to cover is this head fire acceleration and deceleration. I showed already previous case in which the fire accelerates very much and then decelerates. This acceleration is found in different scales. This is a real fire, and you can see that it is somehow possible to explain the rapid acceleration, but the deceleration is more difficult to understand. This is a case of a fire that we had in Portugal, in which you observe these up and downs of the rate of spread, while the wind velocity was practically constant during this period. So it was not due to changes of wind velocity that we had these variations of the rate of spread. And we are now studying this process using the same model for the acceleration. And we see that the deceleration process is also due to the convection around the flow, around the flames. And for example, when we have the acceleration period, we have this very strong wind on this side, but then another wind is created on the other side. And when this increases, the local velocity here is decreased, and this happens very rapidly, and the fire decreases. So we found that the same acceleration model can be applied to the deceleration phase using only a negative parameter here to describe the decrease of the fire. And we have developed the parameters to explain this acceleration and deceleration for a wide range of situations. We understand that for some fires, a better set of parameters should be derived, but we use this as a first approach. And from our findings, we we proposed a model to predict the time it takes to accelerate the fire from one point to the other, or to accelerate from one point to the other. And because this is very, very important for the practical situations. And this is the comparison between the predictions and the observations. And you can see that the model is quite accurate. And as I said, this is quite important for the people to know if the fire is going to accelerate, and then it will more or less stop or decelerate. And for some time, it will be possible to, for example, deploy forces here because the fire will spread not so strongly. These are images from a fire in Mount Carmel. And as you can see, this is a process that occurs in all fires. Even in this fire, it is happening at different points. And you have here this very strong convective column. We found this same process in the fire of Pedrógão in Portugal, in which we had two ignitions, and these two ignitions spread as two separate fires, but parallel to each other. And when these fires interacted and merged, they created a very fast spread here and with very strong convective effects induced by the fires. And in that region, we found the areas in which the fire whirls created by the fire destroyed trees, like these eucalyptus, where we can estimate that the local wind necessary to break these trees is of the order of 240 kilometers per hour. So this was wholly induced by the fire. It shows the relevance of this. We made simulations of the fire also at laboratory scale and compared with the real fires. The maximum velocity in the real fire was of the order of 14 kilometers per hour. And in the model experiments, we found also this rapid acceleration and deceleration with time. Now, to conclude, I would like to remind that the behavior of a fire is a dynamic, and this is due mainly to the interaction between the hot gases produced by fire and the environment, and also between the fire and the vegetation around it, because fire is a reactive process. It is interacting with what exists around it. Recent studies of our team show that the fire behavior is oscillatory, so it has these fluctuations, and this is intrinsically related to a prediction error, especially for large fires. So it is very difficult to predict the rate of spread of large fires based only on the laboratory experiments. What we find is that fire may assume conditions of extreme fire behavior, which are the most challenging for those who have to manage and investigate fires. As Sebastian mentioned, in some cases of steep slopes or canyons or merging fires, we have this very rapid spread, and this modification of the rate of spread, this rapid acceleration, is totally induced by the fire. And the analytical model that we developed, and we are working on it, predicts the time that is required for the head fire to accelerate and decelerate. And it explains that these rapid changes are observed at all scales, and sometimes they are associated to accidents. This is an ongoing research carried out in the scope of FirEUrisk that brings new insights on the understanding of fire behavior, and hopefully will contribute to improve our ability to model and predict it. As Sebastian said, we need to improve the training of the people, of the personnel, and this, I think, can be a contribution in that purpose. Okay, with this I finish my presentation. Thank you.
Thank you, Professor Viegas. Maybe we had a small problem at the end of your presentation because there was a time delay with the slides, but just the very few last slides. So I hope that everybody was able to follow you. And I'm sorry to say that still the next presenter, David Caballero, is not able to connect. So I would like to suggest to move on to the next session, which is the demonstration of the decision support tool that integrates fire behavior model with smoke dispersion model. And I will give the floor to Carlos Viegas.
Hello, good morning, everyone. So I'm gonna quickly share my screen.
Thank you.
I hope you can all see it.
Yes, can you switch to presenter mode? Yes, thank you.
Okay, so my name is Carlos Viegas. I'm a researcher of ADAI, SAFE Group. I'm not an expert on wildfires. My field is actually more into technology, artificial intelligence, robotics, and so on. So lately I've been working on applying these technological tools to fire management, more specifically to predict how the fire behaves and how can we leverage this information to make better decisions and to help us manage the fire, better suppress it, and avoid these dangerous situations that Professor Domingos Viegas and Sebastian have been talking in the previous sessions. So this is part one of two parts of this presentation. I'm going to dwell more on the passing of the mathematical models to computational models and putting this on a decision support tool. And then my colleague, Professor Ana Miranda, she's going to talk about smoke generation and smoke dispersion, which is also a component of this decision support system that we are developing together. So basically, why do we need, why planning and coordination is essential? Because of course, when we have a fire, we need to take advantage of the available means and we need to be efficient because situations change from in a few minutes, in a few hours. They can be, we can pass from a situation that is relatively controlled to some situation that is very dangerous to a lot of people. And so we should be able to predict in advance how the situation might evolve in order to act in advance as opposed to react to what is happening. And in this sense, knowledge and interpretation of data is key. So we need to have accurate information concerning topography, fuel, weather maps, and use this information, leverage this information to have useful data, useful insights, which will help us to manage the fire. And this is the role of fire simulators. So fire simulators are tools that allow us to, based on a set of conditions, topography, fuel maps, and weather, we are able to estimate how the fire propagates and vary some kind of simulation parameters in order to draw some conclusions from these scenarios. And this is very important, as you might imagine, in situations where we want to fight the fire. We want to know how the fire is progressing, where it's going to be in order to manage population areas, critical infrastructures, and so on. I can show you here a video. This was from Portugal this year in September, and this is scary in the sense that what you see here is the fire that is on a highway that has not been cut for the public. So actually the smoke was detected near the highway at 7:05 in the morning, and the road was only closed 50 minutes later. So what you see here is a civilian passing with his car on a highway with other cars around it. He cannot see anything. He has fire around the car, smoke around the car. He's completely disoriented. And this is the kind of situations that we need to avoid. And we should develop the means and the tools to do this. So this is what I've been working for the past 3 years. What you see here is already the tool that we have developed. Here, this is an online-based tool in which you can select the ignition points, or it can automatically fetch ignition points from online sources, such as our civil protection